need to have a quote of the day. This is going to be a broad-ranging quote, and it's going to start with this. Now, what's the story? I started working on PFC 1995, and I got quite excited about this, and I was reading a strange philosophical text since I do those kind of things, and I saw this quote, and I almost passed out. I got so excited. Oh my God, this is a description of PFC. As you will find out, this quote was written in 100 BC. Okay, so a void was made in nature. All her bonds cracked. Look, PFC, right? Obvious. Bonds cracking. This is the introduction to bonded particle modeling. Bonds cracking. Oh my God, that's what I was starting to do with Peter Kundal. Bond these things together. Now let's look at this. Let's unpack this a little. Nature. They have some concept of nature. What's this all about? And somehow her bonds. So this idea that nature is somehow potentially comprised of bonded little things that may be implied in this. So where did this come from? So this was written, is a writing by Lucretius. And so you ask, who is Lucretius? So did I. And this was so long ago that I came around with this. There was no, oh my God, yeah, there was no Wikipedia or internet. So Lucretius, he was a Roman, lived about 100 years before the Common Era, and he was also an Epicurean philosopher. So what does that mean? Where does that come from? Epicurean, well, that relates to Epicurus, and you have to go back another 200 years, and he was a Greek philosopher, and he had all sorts of writings, and he had a particular way of looking at the world and describing the world. And he had many, many followers, and this became called Epicurean philosophy. And the Greeks established a lot of these things. And then 200 years later, the Romans controlled the world and had an enormous empire. And the Romans borrowed very heavily from Greece. They tried to emulate Greece. They felt that Greece was this noble culture. And so it's not surprising then that one of the poets from Rome would have been a adherent of this Epicurean philosopher. And so what did this Lucretius do here? Okay, Epicurus wrote many, many things, but almost none of them have survived. Fortunately for us, Lucretius, 100 years, 200 years later, wrote something which did manage to survive. And he wrote a book, a treatise, an epic poem. It's hard to describe what. It's like 8,000 lines long. And what an amazing title, right? On the nature of things. You couldn't get more broad than that, right? And the thing that's so interesting about this, so why do I know about this? I didn't read this. This was written in Latin. It has eventually been translated. It's extremely difficult to read, I've been told. I read this at the bottom here, okay, by a Harvard historian named Greenblatt, who's an excellent writer. And this he wrote called The Swerve, How the World Became Modern. And he goes all the way back to Lucretius, and he basically talks about this poem and what it was about, and also has an interesting detective story along the way. How is it that this piece of parchment that got written on 100 years ago, 100 BC, which is 2,100 years ago, how did that actually manage to still exist today? And it was a big, long, complicated story. It was almost lost. But notice what that says here, right? When you unpack what they were saying here, their conception of the world, it's extremely similar to the way that most of us, most of like educated Western people look at the world. Okay. And I'm just going to pull out one part that relates to our original quote here about all her bonds cracked. Okay. So you're ready? Just kind of listen to this. I'm going to throw it up here, but let me read it. Okay. So the key element, the way they saw the world, it was made up of invisible particles, everything. Okay. Lucretius, who disliked technical language, chose not to use the standard Greek philosophical term for such particles, but that term was atoms, which meant things that cannot be divided. It's the fundamental thing. You keep breaking something down, you get to these atoms, and you can't make it any smaller. So he used different Latin words, simple words, first things, first beginnings, the bodies of matter, the seeds of things. And the idea was that everything is formed of these seeds and on dissolution returns to them in the end. These things are immutable, indivisible, invisible, infinite in number. They're constantly in motion. They're clashing with one another, and they come together to form new shapes. They come apart, they recombine. This goes on forever. This is a description of molecular dynamics, by the way, of how we can describe the behavior of materials by simulating atoms and molecules and the interaction potentials between them. This is a discrete element method. Mostly discrete elements that Peter Kundal talks about and get attributed to him is simply molecular dynamics at a bigger scale. So the things we're doing, we think of our atoms, our fundamental particles, typically as larger things like sand grains. Guys who are chemists would basically run what they call a molecular dynamics code, which is essentially PFC. But they would actually, their particles would actually be atoms and molecules. And when you do that, you get all this interesting emergent behavior, like when you put H2O molecules together with the potentials of how the hydrogen interacts with hydrogen and how the oxygen interacts with oxygen and things. When you put all those together and run that simulation, you get all these cool things, like you get surface tension. It just like happens, right? It's because of this lower level stuff, right? So there we go. Epicurus, a void was made in nature, all their bonds cracked. So if you're interested in any of this stuff, this is an unbelievably interesting book, this Swerve here. So enough said. Let's big high picture here today. And the last lecture, it's just not going to be next week. I'm going to be in the northern wilderness of Minnesota canoeing. But we'll here. And we're going to cover a lot of material. Okay. And we'll see how it goes. Remember, this is my attempt to kind of refine how I teach this stuff. And there's some new stuff I'm going to be trying here, which also means it might take longer than we think. And if that does, don't worry. The whole idea here is to go slow to make sure you guys can understand things. If necessary, there could possibly be one more lecture after this. So the big picture here, right, we're going to talk about the idea of bonding, and then we're going to talk about different ways of bonding things, which are embodied in 3 different contact models that are in PFC. And we're going to play with these things a little bit, but instead of taking that odometer package and doing this all by hand, as it gets very, very awkward to do, we're going to use a package of a well-defined set of fish functions, a fish modeling environment that's going to allow us to do things like create materials and do tests on them, direct tension, triaxial, things like that. So we're going to use that thing in the process of looking at some basic stuff. And then we're going to talk about, so we sort of now have all the things in place. We have this PFC, we have these contact models, we can like build them and do rock mechanics tests. But now let's talk a little bit about the actual rock. Like, what is rock? What's happening to it? Why does it fail? Let's look at the microstructure of that rock. And that's then going to lead us to a little bit of a description of what this idea of a bonded particle model. Okay. That's where we're going. Okay. Now just give me a second. Okay, here we go. Now I'm going to share my screen. And how do I do this? Give me a second. I did test this. I should know how to do this. Shares. Share screen in 3, 2, 1. And we got it. Can you see the screen, I hope? Can you see all of yourselves?
Yeah, we can see that.
Good. Now, I have to get to this. Are we good here? Can you see the hello, everyone?
Yeah.
Oh, fantastic. Okay, now. Okay, here's the outline a little bit. We're going to pull some stuff together. I just came up with this outline like 15 minutes ago as I was sitting eating my roll and having some coffee, and I wrote this thing on a napkin. But it's going to tie together a bunch of stuff and give you the big high-level picture here. Okay, so we're going to start. Whoops, just a second. I got to turn that pencil on. I think we got this on. Oh gosh, come on, pencil. My pencil has a red light and it's going off. Does that mean I was supposed to keep charging this pencil all the time? Hang on, maybe not. Oh, there we go. Okay, here we go. So of course we have to start with Epicurus, since now you know who Epicurus was, the first guy who kind of prophesized PFC. So here we're going to go from 300 BCE, and we're going to end up moving forward in time. If you remember that early lecture about how does PFC work, it uses two concepts. It uses a concept from Hooke, as in Hooke's law, and that concept is, right? And in the world of PFC, that means we talk about parameter KS, right? Hooke talked about the general idea of stiffness, and if you really think about it a little more, remember I'd like push my finger against my hand, and there's a normal stiffness, there's a shear stiffness. Those are like the two fundamental concepts of stiffness. That's what we have in all discrete element models. That's Hooke, and this is what, about 1690, okay? And then 2 years later, Newton came along, and he figured all this stuff out, F equals ma, right? And so that's what PFC is doing, right? Now, and this is where we're at this point. We've basically been working with this linear contact model, granular material, and remember, we just add to make a granular material now, instead of just having Kn and Ks, we're going to add a friction coefficient, and now we can get the response of a granular system, right? If you remember the key element of friction, if this is delta shear direction, this is shear force, and you start to move things in a shear direction, there's my two particles. That guy can't move. This guy gets moved this way, right? It's going to load up, going to have a stiffness Ks. It's going to reach a critical value, and it's going to do this. And then if we unload, it does that, right? And this critical value, F star, it's a friction coefficient times the current normal force. There's going to be a current normal force, right? Coulomb sliding. So Kn, Ks, and fric, that's the world of discrete elements, and that's granular flow. The only other thing for granular flow is the shape of the particles is important. And if you have all that stuff, this contact model gives you very realistic granular flow. Now we need to talk about bonding, and we started doing that at the end of last lecture. If you recall, we just said let's add a contact bond, which was just like the linear model is, in a sense, you can think of it as the simplest possible granular model. You got to have a normal and shear stiffness, and then if things are going to get interesting, they have to be able to so-called fail. So you have to have a friction coefficient now, and if you just say, let's say they're glued together with a tiny, tiny piece of glue, there's going to be a breakage concept, and they're going to be able to carry tension. And so you're going to talk about, okay, let's just say there's a force, we'll call it the tensile strength, at which it breaks. And possibly if you move it into shear mode, there's going to be a critical shear force at which it breaks. So now you get this concept. You're going to have some new parameters. I'll call that TF and SF. Those are, TF is the tensile force at which it breaks, and SF is the shear force at which it breaks. And this thing, if you recall, is we call this thing a contact bond. That's the contact model. Okay. Now, we're going to find out some things here about, if we start talking about a solid, we don't talk about force and stiffness when we talk about solids anymore. We use concepts of continuum mechanics. And Ayad, is this what you're taking right now?
Yeah, well, I'm still at the point where I learn about tensors and vectors still.
Okay, you're doing this because you know I was about to ask you a question about theory of elasticity, but you haven't got to that yet. Okay.
Yeah.
But continuum mechanics, and when we talk about strength, we don't talk about force, right? We talk about stress. When we talk about a strength of something, it's, you know, as 10 megapascal tensile stress, right? If you do a test in a lab on a bar of steel, here's your steel bar, and it's fixed, and you pull it in a lab, you're applying a force, right? And you measure force versus displacement, where displacement is just going down. And what happens? Initially, it's just linear, and then that steel bar, in this case, it does some crazy stuff. It like yields and things like that. But there's this critical value at which it starts to be nonlinear, and it starts to like fail, right? If this was a rock specimen, this would be easier. A rock specimen would go up and then boom, and it would just fall. It would rupture and the thing would just break apart. Now, when we talk about that, we don't say that the rock has a strength of 10 newtons. What do? We come up with this concept of stress, which is a continuum mechanics concept, and we say, oh, well, we're going to talk about the force per unit area, that's actually the fundamental property of strength, if you will. Okay. And so when we would present the strength of this, we would, whatever the cross-sectional area is here, we would divide the force by that. And then we say, that's it. And in fact, often, you know, this is the lab measurement, but you typically don't even see it that way. You typically plot sigma versus delta. Well, hang on. You also talk about strain in continuum mechanics, which is a way of looking at the fundamental way of how materials behave. As they displace, you can take the gradients of it, and that's what the strain is. And so what typically then, and the strain in this simple test here, if this was the initial length, L naught, the strain, where I'm just talking about axial strain here, right, is going to be delta over L naught, right? And so we typically would present our lab response like this, right? This is what we see. People almost never do this. They always present results like this. Notice they've done a physical test in the modern world. They actually measured force and displacement, but right away in their heads, they're doing a mapping. They're saying, oh, but we're going to pretend it's a continuum, and we're going to think of it as a continuum mechanics problem, and we're going to use theory of elasticity as the fundamental basis of how to express all our results. So there's already been a mapping here. Go into stress strain space. Okay. This was all interesting to me when I started working in this kind of an area, because that's what I thought. Everything is stress and strain. What do you mean? How can you have forces? But actually, it's the forces that are the real things. And this is an idealization of averaging of those forces. Okay. The other thing is, yeah, this is good. This force displacement curve, if we go right there and take the slope, that's the stiffness, right? So here in the actual lab, we're working with force and stiffness. Notice that's what we're working with. See, stiffness, force, we're still back in 1690. Now we come in with continuum mechanics, theory of elasticity. Now we're going to do this. And so what's going to be, just like we take force, but we think about it as a continuum mechanics problem and it turns into stress. If we take stiffness and we think of it in a continuum mechanics way, what does it turn into here? Somebody tell me, what do I put? What do I put there? What do I put there? What's a measure of
Elastic modulus.
Young's modulus. Hello, you get it. E, right? So notice we work force displacement. That's the fundamental world. We have a stiffness, but now we go and treat it as a continuum. And so what we always look at is the ratio, is the slope of the stress strain curve. Because now we're not working in force and displacement. We're like averaging these things. So now we have modulus, right? And there's one other thing that we often do when we're in the lab is we not only, so if we take the spec like this and we squeeze it, and so we apply, let's say we apply a displacement delta. Let's say it's fixed on the bottom. That's easier. Okay. And when we apply delta, we have to keep increasing the force, right? And so as we already showed over here, if we convert that force into a stress and this displacement into a strain, it does this. So let's go and do this here. So we're going to do this, and we're going to get a fundamental quantity called Young's modulus. And let's forget about failure. All materials are very well approximated with linear elastic isotropic material if the strains are small. And so this is the famous Young's modulus, right? And you might remember we talked about Young the other day at the beginning. He was a very bad teacher, but he was a very smart guy. Unfortunately, his writings were preserved. They almost got lost, but there was a professor 80 years after his death at his university who like found all his writings in the university archives and like said, these are awesome. And then he represented them, and that's why we know about them. So we got Young's mod. What is another thing? So if we have theory of elasticity, we have a linear elastic isotropic linear elastic material model, we call this. What do we know about this? Okay, okay, Shihong, I'm going to nail you on this one. You absolutely have no continuum mechanics, at least at a pretty reasonable level. Linear elastic isotropic material. What did the theory of elasticity find people figure out about that? How many material constants are there? Whoops. Did we lose somebody? There we go. Okay. Hey, Shihong, how many material constants are there? You there? Uh-oh.
Sorry.
Okay.
Bad
Shihong,
internet. What's the
here we
question?
go. Oh, okay, here we go. I'm going to nail you on this one. This is your Q exam question, an easy one. If we have a linear elastic isotropic material model, how many parameters are there? To describe such a material, there's two things we need. Sorry. How many are there?
Stress, strain, homogeneous. Constant parameter is EF 等于homogeneous. I think only one.
One. Okay. So here we go. At the beginning of theory of elasticity study, people did this, right? This was the first thing they did. And then there were all kinds of interesting arguments for about 80 years. And the big argument was how many properties do you need to completely describe a linear elastic isotropic material, which is the simplest possible elasticity material. No failure, small strain, no strange, like fibers in the material that are aligned in a certain direction. Everything is isotropic. It's just a hunk of material. It's the same in all directions. And there was a big debate, and some people said one, and some people said two. And the testing ability to do tests with sufficient precision was not available. And so it was not able to many years come up with the answer. Once that testing equipment got precise enough, we did come up with an answer, and the answer is there's two material constants. And what they typically use is Young's modulus E and this thing called Poisson ratio.
Oh, sorry.
Okay. Has everybody at least heard of these two of Poisson ratio?
Yes.
Yes.
Okay. You would have talked about this in your very, very first strength of materials class. So simplest possible. Oh, I like this. Simplest possible discrete element model. Stiffness, force, parameters, Kn, right there, Kn, Ks. Now, simplest possible continuum material is got two parameters, E and nu. And how do they get Poisson ratio? Does anyone recall? Go back to this picture here. There's my little test. And let's measure, if you squeeze this, that's the original shape. And when you squeeze it down, most materials will bulge out like this. Just think of it, take a pencil eraser, take a big hunk of anything that you can squeeze, so it'd have to be like a big pencil eraser, push down on it and it bulges out. That makes sense? Push down and stuff, it bulges out. Are you with me? That's what we see. Okay? Okay?
Okay.
Okay. So what did we do? We started from this state. So this had an initial length, and this also had an initial length in that direction. And we define the strain, the axial strain. So let's make a coordinate system, x, y. So the strain in the y is the delta that we applied divided by L naught, right? And the strain in the x is going to be, so that's delta x over little L naught. So basically the strain in this direction, and then we've got other strains. So we apply strain in the y direction, and the result is the material bulges and gives us a strain in the x direction. You with me?
Yep.
Okay. And notice if we make the strain in the y, we compress it. We're going to have a sign convention, and we're going to say that extension is positive, tension is positive. Everyone in mechanics does it that way, except rock mechanics. So if we do that when we squeeze something in the direction, that's a negative strain, but it bulges out. It's a positive. Okay. So people then said, oh, this is a fundamental property of the material. If I apply a delta y to something, what's the resulting delta x? And they said this is a fundamental thing. Just like if I apply delta y, I can work out this. There's a stiffness, right? That's fundamental. If I change the material, it gets more stiff. And so I can measure that with Young's modulus. Well, if you then hear, you say this ratio, they define this quantity called Poisson's ratio, and it's minus delta y, not delta, strain in the y over strain in the x. It's the ratio of how much it goes out versus how much we squeezed it down. And so if we were to plot, gosh, what do we got to do here? Stress and strain, E is. So let's go back here. E is delta sigma over delta strain. And nu is minus strain in the y direction over strain in the x. So this would be delta y over strain in the y. And this is delta y. Okay, so if we plotted, what did we got to plot here? If we plotted strain in the y and the resulting strain x and plotted the negative of that, it would do this. And this is the slope, Poisson ratio. Okay, so if a Poisson ratio is 0, it means we squeeze it down, it doesn't bulge at all. Very few materials do that. In most cases, when we squeeze it down, it bulges and they have a positive slope here. Okay. So in the world of continuum mechanics, we're going to characterize elastic response in the simplest possible way with the Young modulus and Poisson ratio. So this gives us a problem right from the start here. Now, if we start bonding together these simple models that just have stiffness, Kn, what the heck? How are we going to figure out, for example, if we want to build a bonded system that has a certain Young's modulus and Poisson ratio, what are we going to do to choose Kn and Ks? So the system of particles with springs, it's going to deform in a certain way, and the deformation is controlled by Kn and Ks and the shape, remember. So, you know, if you may recall, there was that picture we showed of that physical system of tennis balls joined by springs, right? And so that model, when we squeeze it, it's going to bulge out, right? So we could measure its Poisson ratio. So what we're going to do here is, turns out that if we make simple packings of particles with simple shapes, like let's say we do this. We take disks that are exactly the same size and we perfectly pack them like this, and we do a UCS test. We just do this, right? And we apply delta and we measure the force, right? We can do all this with PFC. And notice this force is the total force because it's going to be made up of 3 little contact forces, right? And so if we do this and we plot and we take force and we divide it by this area, we can call that stress. And if we take delta and divide it by this, we can call that strain. And we can plot this and it does this, and we can go here. We can measure E. And so that's great, but that's for the whole entire assembly of things. But let's think about this system a minute and say, well, kind of a fundamental unit here is this. Because here's another fundamental unit, same thing. And I think you can see here is that there's a fundamental unit. They're all the same. And if you put all those fundamental units together, it makes the whole. So if you just look at that, okay, this in a DEM model is modeled as a particle, and a spring with the stiffness. Are you with me? That's what the DEM model would be, right?
Yes.
Okay. Now we could say, well, I'm going to pretend though that it's actually just going to be this. What if it was this? What if it was, I'm saying, instead of thinking of this as a spring, let's assume that this was this was a linear elastic isotropic body. And let's just make up a new thing called an effective modulus. Okay. And can I relate this effective modulus to this stiffness? Because if I can look at this big system over here and I can say, oh, well, the big system's going to be behaving like the little system, and it should have the same relationship. So think of it also this way. What do we do in our discrete element model? We apply, say this guy's fixed, we apply a delta and we measure a force, right? So at this level, this little hunk of a material here is producing this, right? If it's a black box, all I do is I look at this chunk, I make these guys move together by delta, and I get the force out. And if I got that, and I don't know what's happening inside here. All I know is I did this experiment. I took these two guys, I applied delta, I measured force, and I divide force by an area. So this thing is going to have an area, and I get stress. And if I call this L naught, distance between the centers, I can get a strain. And so I just measure this. I run the DEM model. I don't know what the hell's in there. Something is in there, and it's letting me produce this. So I could then go and take that slope. I'm going to call that E star. Now I could also have, I'm thinking of black box in the sense of, to get this result, I could either, there might be a spring in there, but there might also be a hunk of elastic material. And so if there was a hunk of elastic, if there's a spring in there, it's just K that we care about. But if there was a hunk of elastic material in there, oh, stop this. It's E star that we care about. So then the question is, if you have a cylindrical shaped hunk of elastic material, it has an effective modulus E star, it has a cross-sectional area A. Can you relate that to a stiffness? And let's see, the answer is going to be yes. Let's see if we can. We know that stress, in this case, equals E times strain, where that's the, call it E star times strain. Well, stress is going to be force over area is going to equal E star, and strain is going to be delta over L naught. So that's going to be delta over L naught. Okay. Now let's rearrange terms. Let's bring the A to the right and the delta to the left. So I'm going to get F over delta equals E star times A over L naught. Are you with me? Everybody with me?
Yep.
Yes.
Yes? Well, now if you notice F delta, it's a straight line. This is stiffness. So by definition, stiffness is F over delta. So this is actually stiffness equals E star A over L naught. So this is our mapping between, if these were both equivalent systems, either a spring or a hunk of elastic material, you would either have to have, there's a relationship to get the same force displacement response. There's a relationship of a K or a E naught, and it's this. So this says that if I were to say, I'm going to give you a E star, think of that as the parameter. If I take that, and remember, this is this little area here, this little hunk. If I take that, multiply it by the area and divide it by this length, that's going to give me a value for K. And this will be the Kn. And if we go back to this system here, you can convince yourself for this system where it's perfectly lined up that the behavior of one of these is going to be the same. When you put them all together, it'll give you the same big time behavior for the whole ensemble as it will for just one. So the result is going to be then that if we build this type of packing, if we say the parameter is going to be E star, so we want to make the system have a certain Young's modulus. If we take that, multiply it by A over L naught, which we know, that's what we would set the stiffness to, Kn. And so, again, if we had this system, and we could build all this and verify this easily in PFC, put these perfectly together, specify a E star, 10 gigapascals, and now that I do this analysis again of this thing. So then, stop this. So, you know, the area, right? If this ball had certain radius, the area, stop this, in 3D would be pi r squared. That would be the area term. The length would be this, which would be 2r. And so for this system then, we would set K. If we set K to that value, and if we simply then did this test and measured force and displacement at the macro scale and made this plot, by using that K, if we turned the plot into a stress strain, it would have that modulus. Okay. So this is the first step. There's two steps. We have two elastic constants, Young's modulus and Poisson ratio. Here we have a way of coming up with an approximate relationship. If you want to get a certain Young modulus, you use this expression here to figure out how to set K. And it's just Kn here that we're talking about. Okay, is everyone with me? Kind of with me? Ask me questions.
I do kind of have a question. Maybe I missed it.
Sure.
So when you put stress equal E star strain, and then we went and said stress is F over A.
Yes.
So this area, like when we take the macro scale, is it the same when we take the micro scale? Because we are talking on the area or like an elastic region between two particles now. So I'm just confused, like if this area is like the whole thing or
Boom. Super good. You're not confused. That's the next thing. Okay. No, in general, the answer is no. In general, this does not account for all the area properly. Okay. And this is why I was saying for this particular system that has perfect disks, okay, for this system, we can work out this relationship for one little hunk. And the relationship for a little hunk is always the same. Okay, so this would, if it's 3D, we could assume that between the two, if they're a radius, right, we could assume this area is pi r squared, and that length is 2r, right? And what we find is if we do this analysis, if we use this expression, this is the thing. If we use this expression, it will give us a first pass value of Kn. And what we will then do is use that, do an actual packed system, and do a small strain test and measure the slope, measure this slope here, and we'll actually measure the E. And what you will find is for a general system that will be close. We might be within 10 or 15%. And that then means, oh, okay, if we need it to be 15% more, we're just going to do another test where we multiply this by 1.15 and we run it again. And when we run it again, we should have the E that we want. Okay?
Okay.
And even for the 3D case, it doesn't work because we're modeling, we're conceptually thinking of this as a cylinder. And if you line up all those cylinders, as you've aptly pointed out, that's not filling up the space of a big giant cylinder, right? Because we're modeling a bunch of small cylinders next to it. Theoretically, we're thinking of it as a bunch of small cylinders lined up, and that doesn't account for all the volume. Okay. But this is a reasonable starting point, okay, to try to come up with a value of Kn. Okay. And notice it'll be different. If you have a different radius, you're going to have a different area. And so you're going to have to choose a different Kn. Okay. Now let's go to the Poisson ratio business. Here's what, think about this. This is interesting. In this system where they're perfectly lined up, and problem is you can't see me pointing at things, so I have to keep doing this. In that system, if I applied this boundary condition and just pushed it down, how much would it bulge out? Because if we apply a delta this way, sorry, uh-oh. Oh, come on. Don't tell me that my pencil is dead. Oh, come on. Oh, we're almost out of pencil time. Uh-oh. Oh, this is terrible. Hang on. I don't have a backup pencil. Wait, one last try here. Okay. Okay, my pencil has died and I cannot recreate it. So we're going to have to fall back to doing this in PowerPoint. So let me stop sharing the screen.
Well, or maybe you can try to use your fingers to draw that.
Oh gosh. Yes, you could be. Hang on.
Yep, I think it could be setting in the setting app.
Yes, I think I can. Just a second. Let me first try that here. I think I read about that somewhere. So I have to somehow set that. Oh gosh, where do I do that? This is Notepad. Does anyone know where I make that setting? Let me, hang on, you guys can help me here. Let me
I
share
think the
this.
setting in the like original setting of the device on accessibility, if I'm not mistaken.
Okay. We're going to find out. Let's see. Share screen.
Or are there any choice like Apple Pencil, and you can
Yep. Yeah.
set.
I think you're right. Hold on. I want to get this. Now you got my screen. You guys can help me figure out where to go. I'm not a Mac guy or an iPad guy. So I'm going to go to settings.
Yeah,
And
then
help.
press the Apple Pencil
Here we go.
and
Take that off. It says only draw with Apple Pencil. I took that off.
yeah,
So
and
now I'm assuming, come on, or is there something else I have to do? Let's see. We got it. Brilliant. Good job. Thank you. Oh, except now, how do I move the? Okay, so as you can see,
2
I can
fingers.
2 fingers. Oh my God, you guys are great. Okay, here we go. Thank you. As you can see, I'm making this all up on the fly, but this is important, and I think you're following me. Otherwise, I show you like 2 slides. Boom, here we go. And what the hell is he talking about? Okay, going back to this system here, right? If I were to push this thing down, how much would it bulge out? This PFC model. Any ideas? It's perfectly lined up. What if I simplified it to just this? And I applied delta. How's it going to deform? What's going to happen?
They're going to slip
They don't slip. Nope. Where are they going to move? How are they going to move? What direction?
to horizontally.
X, Y. They're only going to move in the Y, right? They're going to end up looking like this. And so they're going to end up looking like this. Well, I'm not doing it right, but, and there will be an applied delta to that, right? So that means delta X would be 0. That's if I just had 3 of them. Well, what if I took another 3 and put it right next to them? And I did the same thing. Each one would just go straight down. So if I did this system perfectly lined up and pushed it down, it would only move straight down, which means, remember, Poisson ratio that we measure is minus, again, this is going to be X, this is going to be Y, minus strain in the X over strain in the Y. Strain in the X is 0, so therefore this material is going to have a 0 Poisson ratio. And that's actually what would happen. Just think, if you took a bunch of marbles and you perfectly lined them up, you pushed them down, well, each one just forms a column. It's perfectly balanced column, so each column just goes straight down. There's nothing that wants to make it bulk out. Are you with me?
So I think about it, if there is no confinement, then they will slip.
There's
Right?
no slip here. We're doing small strain.
Okay, yeah.
Okay.
Yeah.
And think about it, because they're perfectly lined up, they're only going to slip if a shear force builds up. And a shear force is only going to build up if there's relative shear motion at contact. This contact does not have any shear motion. This guy never moves this way or this way. And this contact also, they both move down the same amount. So therefore, there's also no shear motion there. And so they can't slip.
Okay. Thank
Okay,
you.
good point. So this is this interesting case. Now, what if we did a different system? What if we made a packing that looked like this? I'm going to line these up perfectly. Then I'm going to duplicate that, and I'm going to raise it up, but I'm going to move it over so that now it looks like this. And then I do it again. This is called, I think this is called a hexagonal close pack. Do you see do you see the idea of what I'm doing? This also perfectly fits together. Okay? With me?
Yep.
Okay. And I could replicate this, and I could make an infinite packing of this, just like I could have made an infinite packing of that as well. So this case now what's going to happen if I push it down? Think of putting that in front of you. You're drinking a coffee or a beer, and you got a whole bunch of coins, the same coins, and you lay them on the table in front of you, just like this. And now you push them together. What's going to happen to the coins? How are they going to move?
So now they will have both delta x and delta y.
Exactly. So there's going to be, again, coordinate system x, y. There's going to be this, again, Poisson ratio minus strain in the x over strain in the y. Now this guy, it's going to go this way, right? And depending on how much it goes that way, relative to how much you pushed it down, that gives you a Poisson ratio. And remember, this value is going to be negative. So this the y is a negative number. This one's going to be positive. So you have a negative sign there. So you get a positive Poisson ratio. And so if you did coins, I don't know, I haven't done it. You'll probably get something like 0.4 or something like that. Typical rock is between 0.2 and 0.4 maybe. Okay, so are you with me so far?
Yep.
For this packing, the crazy special singular case. This is like this weird perfect alignment. If you perturb this packing pretty much in any way, and this is a very simple perturbation of it. It's an organized perturbation of it, this guy. You push this, it's going to go out. It's going to have a Poisson ratio. Okay. And also, if instead of this, but you now took a general size distribution of spheres or disks, and you packed them into a cup, and then if you squeezed it, because it's an arbitrary packing, everything doesn't perfectly line up, you are going to have a bulge out, which means you are going to measure a Poisson ratio. Okay. Make sense? Okay. And the same thing would happen. This is, again, the PFC thing. There's nothing PFC, there's nothing numerical about this. This is fundamental. Particles push it together. So if you had sand, a bunch of pellets of sand, and you put them in an odometer test cell, and then you cemented them, as long as the sand grains don't perfectly line up, that's a cemented thing now. When you squeeze it a little bit, it's going to bulge out, and it's going to have a Poisson ratio that you can measure. Okay. And that Poisson ratio is going to be a function of the shape. It's going to be a function of how it's packed, right? This guy, the shape is the same. The shape is a disk, but if it's packed in this way, it has a 0 Poisson ratio. Same shape, packed in a different way, different Poisson ratio. Make a slight perturbation of sizes for this guy, pack it, it would be one of those arbitrary packs like we always have been looking at. It's going to have yet a different Poisson ratio. Okay. Now, this is remember, we're still thinking. So this is what's going to happen. This is what we see. both in a real material and in a thing. This is actually telling us, where does Poisson ratio come from? Why is there a Poisson ratio in a real material? It's that a real material has to be somehow glued together. The constituents of it have to be glued together, because otherwise it's not, we don't think of it as a continuous thing, but then we think of it as a granular material. So it has to be somehow glued together. And the Poisson bulging out effect is related to shape and the packing. And it's also going to be related to the KS. So this granular material in the granular world, the two key parameters for elastic response, there's no friction here because it's not sliding, it's not failing, it's just elastic. As we've argued here, that the fundamental thing is a stiffness between the particles. So it has a Kn and a Ks. And so far, we've said that we can estimate Kn and relate it to the to a modulus EA over L by doing that. And that's a pretty good, that's going to get us close. Okay. Now, there's also Ks in here. Notice, first of all, as AI, when she asked about, for this system, she asked about friction coefficient, and we reasoned through and said, well, there's no relative shear motion here, so friction coefficient doesn't matter. That also means if there's no relative shear motion, you're not going to build up shear force, because, oh, come on, because shear force, right, for the simplest possible model, shear force is equal to shear stiffness times shear motion, relative shear motion, right? So if there's no relative shear motion, this doesn't matter. This parameter is not coming into play. But as soon as we perturb this thing, and let's say we do this now there's going to be all kinds of crazy shear motion at all these different contacts. So Ks is going to play a role in how this material transfers load. And the way it transfers load is the way it pushes against each other, and the way it pushes against each other is making it deform. Okay? Everybody with me so far?
Yep.
Okay? We're on our path here. Poisson ratio. Here we go. Look at this. So the question now is there a way, can we do some kind of simplified analysis to somehow relate this to Ks? This is the question. That's my question mark. Okay. And maybe even also Kn. I think it's probably going to be it almost for sure has to be a function of both, because as soon as you have an arbitrary system here, both Kn and Ks are coming into play. So see, now if this was, we really were having a graduate student course here, I could stop now and I could say, this is your problem. Think about this. And if you thought about it enough and you looked at it the right way, I bet you could work this out. We're going to do it right now. So for the modulus case, we said, let's take that as the fundamental system, two particles, and let's talk about a hunk of material. And based on that system and its behavior, we were able to relate the E star to the Kn, right? That was the fundamental system. And notice now, this system does not bulge out, and it has no Ks, doesn't matter, and that's why this E star is related to Kn, and there's no Ks involved, and there's no Poisson ratio effect. So this system is too simple. It will not give us a Poisson effect. What do you think we could do, though? What system? How many particles would we need, and how would they have to be arranged so that we could get a Poisson effect? Think about this. Is there a fundamental unit of a certain number of particles that we could replicate an infinite number of times to create that packing? Is there a fundamental unit? And what is it? What if we look at this guy, this guy, this guy, and this guy? If I took that, I could replace it and I could stick it to the right and up, and I could fill the space if I use that as my unit cell. So if we could figure out what's going on with that system, if we took that system and made an infinite packing of it, it would behave the same at the micro scale and the macro scale. Just like for this other one, whoops, oh geez, what happened? What happened? Are you still, am I still there?
Yeah,
You
you're
guys-
still
are, but not
here.
your screen.
Yeah, I'm looking at this. My screen is, what the hell? I still got 84% power.
Maybe
Okay, hang
try
on.
share it again.
Okay, hold on. If we're lucky, I should still be sharing. I got my screen back now. I'm gonna go back into, I'm gonna try to share it again. Share screen. Share screen without audio. Start broadcast in 3, 2, 1. And maybe, come on. Oh God, is it going? I don't think it's going. Is it going?
Yep, we can see it now.
Yes.
Okay, something weird happened, but we're good. So in the same way that this, whoops, so you can see it. Okay, the same way that this system, if we looked at that fundamental unit, we could reproduce it and it give the same macro and micro. We can do the same thing if we're exploring KN with this system. So here we go. Disks, perfectly, I'm gonna try to draw this, trying to make a symmetry line. One of them is here, one of them is here, and this one is exactly lined up here. Okay, do you get the idea? This system. Now, and it's gonna be perfectly aligned, and remember, it has to be bonded so that we get this solid-like elastic behavior. So first, the contacts. There's going to be a contact there, and there, and there, and there, and there. You agree?
Yes.
Yep.
Okay. Each contact is going to have a Kn and a Ks. Friction coefficient doesn't matter because it's small strain. So you agree with that too, do you?
Yes.
Okay. Now what are we going to do to this system? We're going to fix this guy. And this guy, we're simply going to make it move down by delta. And what do we expect? We're going to look at this guy and this guy. So this is delta naught, which is 2r. And when we push this down by delta, we're expecting again, x, y, that's delta y. Do you agree that we're expecting when we push this down by delta y that the two side ones are going to move out with the delta x?
Yeah.
Okay. And then do you agree if we did that, that means we have measured the Poisson ratio. And again, it's minus, well, we would have to define then strain in the x as delta x over 2r. And we would define strain in the y as delta y over, in this case, it would have to be this distance, which we could work out. Let's just call it Ly. Are you with me? We could make that, that's a function of radiuses for this system because we know the arrangement and the geometry, right?
Yes.
Okay. Oh, and in fact, it's since this is so, well, let's not worry about it. And no, it's not just 4R, but we could write that. So if we did that, when we computed, when we did this minus this over this for this system, Kn and Ks, right? This is now where I say, okay, there you go. I've just defined the problem. Go work it out. Okay. And I bet you guys could work it out. But we're going to work it out here. Okay. We're not going to work it all the way. We're going to show the general idea. So again, let's look at this more closely. There's that one. There's this one. There's this one. There's this one. Now let's think about this. This guy, we could look at that contact. And if we solve the problem for that contact, there's symmetry here. So if we solve the problem for that contact, we've actually also solved it for that contact. And there's also symmetry here. So we've also solved it for that one and that one. Are you with me?
Yep.
Get the general idea here. And then there's also going to be a little bit of something going on here. Okay. So the question is, if we apply this delta, this guy can't move. For the first time step, we apply a small delta. There's going to be some sort of overlap that's going to develop here, a relative overlap. It's not going to be in the normal direction. It's going to be in this direction. And we should be able to decompose it into a normal delta and a shear delta. So is everyone following me still?
Yep.
Yeah.
Okay. So I'm making this guy go down by delta. And if you look here, so what's going to happen? I'm going to take, I got to draw this more carefully. Call this guy A, call this guy B. So let's look at B again. B, and here's A. So A is going to move down. It's going to move. Look at this. If I look at the force, at the motion, the relative motion, so there's going to be, if I draw it properly, it'll be obvious. Like this, there's going to be a motion delta, which can be decomposed into a delta normal plus a delta shear. You with me?
Yep.
Yes.
Okay. And we could work out the geometry of this because it's just a function of the radiuses and these angles and things. Okay. Now we don't have to do any math. We've got the key thing here. Let's now look at, so let's talk about the force acting on a force called Fn, pushing it this way. And this guy is going to produce a force Fs, pushing it that way. Because if we multiply the delta n by Kn and the delta S by Ks, we get the forces, right? Yes, right?
Yes.
Okay. So again, my system, A, B, C, D. So we're looking at this little point of the surface, and notice it has a force going this way, and it also has a force going this way. All right, let's not even worry about writing Fn and Fs. And this guy, C, which I'm going to just draw over here, since it's symmetric, over here, this guy has an Fn and an Fs. And they're the same. They're just equal and opposite. So this is Fn for both cases, and this is Fs for both cases. So these are the forces here acting on C, just this top part, okay? And these are the forces acting on B. Now, look at what's going to happen in terms of the Fn forces are pushing these guys apart. Do you agree? The Fn
Yes.
forces are pushing them apart. That's what we're expecting. These Fs forces, though, are actually pulling them together. Do you agree?
Yes.
Okay. So let's think about this now. Let's pretend that there was no Fs. If there was no Fs, these guys would for sure push apart. Okay. Let's pretend there's no Fn. If there's only Fs pulling those suckers together, they're going to move together. You see that? The shear
Yes.
force is actually pulling those guys together. The normal force is the one that's pushing them apart. Are you with me?
Yes.
Okay. Well, what's Fn? What's it related to? In this system, we're applying delta. So Fn is equal to Kn times this relative. It's this delta n. It's this guy here. That's what Fn is. And Fs is Ks, and it's times delta S. Now, this is getting interesting. We're applying delta. We're decomposing it into delta N and delta S based on the geometry. And the stiffnesses are coming in here, okay? Think about this now. We were trying to reason, what if Fn is huge and Fs is small? Well, that means if you make Kn huge and Ks small, that's what's going to happen. Fn will be big and Ks will be Fs will be small. Stiffness draws force. More stiff, more force. So the boundary condition here is we're applying delta, which is directly then giving us delta N and delta S. So the value of Fn of these Kns and Ks's is going to determine how much load is going in the normal direction and how much load is going in the shear direction. And so we could talk about the important thing is really the ratio of Kn to Ks. Let's call this kappa. If this kappa is really, really big, that means Ks is approaching 0. If kappa is really big, we pretty much just have Fn pushing it out. And it's going to push apart. But at some point, as we start to make Ks bigger compared to Kn, we're going to get rid of Fn and we're just going to have Fs acting. Okay. So we also can say, so if we have kappa, let's make this be 1. This is bigger, let's say 10. This is smaller, 0.2, 0.2, right? That means that if we make this, it's possible that this Fs effect might get bigger than the Fn effect, which means they're going to pull together, which means they're going to have a negative Poisson ratio. And so this ratio is important. So if you could build a material that had no normal stiffness but shear stiffness, you're now going to have a system where this particle is getting loaded like this, and this particle is getting loaded like this. That's what happens when you're way over here. When kappa is really small, that's the system, which means when you squeeze it, these two guys are going to move in. Let's stop. Are you with me? Does this make sense? I feel like I'm doing a magic show here. First of all, does this make sense? This makes sense. Okay. It's super interesting. It means that if you could, the picture I always have in my head is 3 coins stacked up as a triangular shape, going way back. There, I think of these coins, these guys, and if I push this down, they push out. And so for the coins, for the case of the coins, that system has a huge Kn and a super, super small Ks. Okay. If you could somehow build a material that had a very low normal stiffness and high shear stiffness, and think this is a weird material. Think of the holding out your hand in front of you again and pushing your finger on your back of your hand. Most materials have a higher normal stiffness and a lower shear stiffness. But if you could somehow build a material that had a high shear stiffness, it would actually give you a negative. So when you squeezed it, it would contract. Okay. And there actually are such materials in the real world. And they're very exotic. They have interesting, strange internal microstructures. But fundamentally, they end up having these high shear stiffness versus low normal stiffness. Okay. And so what this is saying then, and notice this system, which has the ball here, the set of 4, it's doing the same thing. It's symmetric. So I could do the same analysis I just did, pushing this guy up by delta, pushing this guy down by delta, and these forces, all 4 of them, these guys would all be the same, and the same analysis is applying. And the key thing is, are these guys going this way, and are they going more than the Fn? The Fn is pushing them apart. The Fs is pulling them in. Okay. So everybody with me? One last thing to tie this all together. Let's think about this in terms of force chains. Because force chains is how real materials, that's why they behave like they behave. And it applies to solids just as well as granular systems. This system, remember we talked about, if we talk about this guy, he's got Fn, he's got Fs, and if you take the result, you get some sort of a resultant force. So this guy, B, at this contact, A, has a resultant force, and we could draw that as a force chain. And so that force chain, if Fn is bigger, that resultant force is going to end up pointing this way. So we're going to get a force chain that looks like. But as we change that ratio of Kn to Ks and keep making fixed Kn and keep making Ks bigger and bigger, eventually this force chain is going to rotate. because eventually it's going to have to reach a point where it's going this way, because, right, this guy and this guy, there's going to be a force chain going that way and a force chain going that way. The result is these guys are going to move together. Are you with me? If we think about this in terms of force chains, sort of,
Yes.
okay? And so there's going to be some value here. Notice it's slowly changing as I vary that ratio. There's going to be some, I'll call it the magic ratio, at which force chain will go straight down and straight down, straight down and straight down. There's going to be some magic ratio. And if the force chains go straight down, what's going to be the Poisson ratio? Think of just one of these, B. B would look like this, and it would have a force going there and a force going there, and they line up.
Zero.
There's no component of force on this guy that is in the X direction, which means this guy's just going to sit there, and it's not going to move in or out.
So it's 0.
So it would not move in or out. Correct. So the Poisson ratio would be 0 for that magic value of kappa. And the other side, this guy is going to be pushing this way and this way. That's going to be a positive Poisson ratio. And for the other side of that magic value, it's going to be pushing this way, and that'll be a negative Poisson ratio. So there's going to be kappa. What's kappa? It's the ratio of Kn to Ks. And this is going to be Poisson ratio. And so there's going to be a certain place where it's 0. Let's talk about Poisson ratio. We go back to fundamental theory of elasticity. When we talk about how bodies deform, if we have a linear elastic isotropic body, the complete deformation is determined by two parameters, two properties, E and nu. And you can look at these systems in a fundamental way, and you can think about, if you force this little hunk of material to deform, how is it going to strain? And if you know E and nu, you know how it's going to strain. You squeeze the boundary in some way, and you can figure out the distribution, or you apply a load to the top and bottom, and you can figure out how it's. What theory of elasticity will tell you. It relates the stresses to the strains. And you can then do energy thinking with this, and you can talk about, if I push a hunk of material and squeeze it, I've done work on the boundary, and that's energy that I've applied, and that energy is actually going into deforming the system, and we call that strain energy. Okay. And so by doing these energy thinking about stuff, you can find out things like, well, if I apply energy to the boundary, it has to get stored in strain energy, okay, somehow. Based on doing all of that, what people can show for this theoretical material, which is a linear elastic isotropic material, is that Poisson ratio has to be between, the highest it can ever be is 0.5, and the lowest it can ever be is -1. So if you have a linear elastic isotropic material and you measure its Poisson ratio, it can never be outside of that range. It's impossible, okay? And so first of all, this is telling us, okay, it's okay that we can have negative Poisson ratio. Many people don't know this. Many people assume, oh, Poisson ratio has to be positive. Otherwise, it doesn't make sense. But there are materials that have negative Poisson ratios. They really exist. And theory of elasticity confirms that they should exist. So that's the thing here. And so the question now, it turns out, is what is that magic value of kappa? So if kappa is really big, we get some positive Poisson ratio. if kappa is really small, we get some negative, and there's got to be some relationship here between them. And I don't know if it's linear or not. I would speculate it's probably linear in this system, but we don't know for sure. But all we know is when it gets really big, there's some magic value. When it keeps getting bigger, this keeps getting bigger. And when it gets smaller, this keeps getting smaller. That's what we know based on just this fundamental reasoning. We haven't even written any equations except F equals K delta. And see, now I really should stop and say, okay, go off now and solve this. And at this point, I'm sure you guys could also, I really do believe it might take multiple hours, but all the ingredients are here for you to solve this because you know everything. And if you use the geometry, right, you apply delta, you can write what delta N and delta S are as a function of the packing, the radius, and the angle there. You know Kn and Ks, you can express this, da, 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 da. You could work all this out. And if you did, you would find that Poisson ratio is 0 when, anybody have any guesses? What do you think is the magic K, kappa?
Well, I think it's 1.
Think it's 1. Why?
So I think when they are equal, Kn and Ks, that's when we will have straight line in the chain force, as we saw.
So that is correct. And I just realized you could actually do, that's exactly right. You could just write those equations right now because it's just based on this angle. It's based on this angle here of these things. I think you're right. Yes. And if you had, since this is for whatever, you're right. That's what it is. So you would have a Fn and you would have a Fs, and this is the total F. And so go ahead.
So if we do geometry, we will do two equations, right? Like one Poisson's ratio is positive and then negative, and we will end up with kappa equal 1. Supposedly.
Correct.
Yes.
Okay, and so this magic number is 1. This is super interesting and remarkable. So what's this telling us? Let's go back. That means if we take this system, this particular, it's like the simplest possible system I can think of that we can get this effect, right? It's this hexagonal pack business. And if we do this boundary value problem in any discrete element code, and we apply delta, and we simply look at the force chains, if they go straight down, that means what's going to happen is they're going to go like this, right? This magically. And if all the force chains do that, it doesn't bulge out. So Poisson ratio is 0, right? And in the other case, they're going to start pushing out. They're going to look like a thing like this. We'll see these things, and then it's going to bulge out and not bulge out. And you can run easy enough. It's trivial to build this PFC model. And you can look at those force chains and you will find that it's like magic. They actually go straight down and Kn over Ks is 1. And I just got to show you this because it's like so cool. And stop sharing. Tell me if you can see my screen again. Oh, screen size. Now, hopefully you can see my screen. Can you see my screen?
Not yet.
Oh, come on. You can't see my screen. What the, oh, okay, because that means I have to share my screen on this one. Thank you. Now, got it. Can you see my screen?
Yes.
Awesome. Okay. This is now, if I hadn't spent 45 minutes talking to you, I would only show you these 6 slides and probably wouldn't have any freaking idea what I'm talking about. Here we go. You should be able to understand these slides now. This is the tying everything up for this part of what we're talking about. There's our discrete element system. As we talked about earlier, if we push down on it with a force, we get a delta. And in a real world, you get a single baseball. If it's a material, it's going to not only contract, it's going to expand, which means if we just looked at a single baseball, and if it was a linear elastic isotropic body, it would have a Poisson ratio. It would expand. We would measure a Poisson ratio. So apparently baseballs are like normal materials. They have positive Poisson ratio. And so this is what it would look like. But we're going to go and we're going to model it this way by putting springs in at the contacts. We're going to let things overlap. So we're saying that the particles don't deform. They stay rigid. It overlaps. And we're putting in a spring, Kn. This is the beginning. We haven't talked about Poisson ratio yet. And this is now the question of how the heck do I choose these stiffnesses? And they can be related to what I'll call an effective modulus of an equivalent continuum. So this picture, what if we had this picture? And this would be a cylinder of a linear elastic isotropic material. It's characterized by a height, by an area, and by a E star, right? And notice, if I'm this guy and I'm pushing down on this, if I don't know what's inside there under the hood, it doesn't make any difference if it's springs or if it's this. It's still going to behave the same way. That's the idea, right, behind all this. And we can show that this stiffness is related to AE over L. Okay. And so this here, this is the derivation. Remember I said stress equals E times strain. Stress, force over area. Strain is change in length over the original length. There's the original length. Bring the delta to that side, the A to that side. By definition, this ratio is stiffness. And there's our magic relationship, right? And in order to do this for an arbitrary system, here's an arbitrary system of particles, we're going to have to assume what is the shape, what is the volume of material that we're going to think is this idealized, what if it was a linear elastic isotropic material. So here's what we're going to do in PFC by default. We're going to take two particles, and we're going to take the smaller one, and we're going to pretend that that's material. It's this gray thing. And once we do that, now we know what L is. L is the sum of the radiuses, right? This is the 2 times that radius, right? Da, 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 da. If it's a wall and a ball, we're going to use the ball radius, and we're going to make that be the hunk of material. And again, if I take an arbitrary packing and draw all these little things, they don't perfectly fill space. So this is an approximation, okay? And so therefore, it turns out we're going to have two parameters to describe a bonded material. We're going to have a effective modulus, and we're going to have this normal to shear stiffness ratio, which I've been decided to call kappa. Okay. And first of all, what's going to happen is because the model doesn't know about E star and kappa, but the model knows about Kn and Ks. So given that you specify an E star and a kappa star, it's going to use these two equations to set Kn and Ks. Kn, that was that first analysis. It's just AE over L. Boom, now you got Kn. And this, I don't know, kappa is this magic thing. So if I know Kn, and if you tell me the ratio of Kn to Ks, then I know Ks. Okay. And what we're going to find is that this kappa star, this is what we're going to find. Here's an assembly bonded. We squeeze it. We apply it. There's, this is a general biaxial, triaxial test, right? You squeeze it, you apply velocity, you have confinement, right? Whatever. If we measure now the macroscopic E of this, it's going to be linearly related to E star. So as E star gets bigger, we'll find out that the measured E gets bigger. And we're also going to find that the Poisson ratio of this overall assembly is related to kappa star. And this idea that as you keep increasing kappa star V, eventually Poisson ratio will limit itself out. You can't just keep, there's going to be a kappa at which if you make it any bigger, it doesn't affect anything anymore, because basically all the load is going into the FN. And when you do all that, you'll end up measuring a Poisson ratio that will be like 0.5. And so that's why I said it goes to a limiting value. And this is the magic picture. Now you should understand the idea, right? Here's our unit cell. We have forced the bottom and the top to directly move. All the bonds are intact. It's a small strain thing. Notice black is compression, red is tension. I squeeze, in this case, those force chains have a shear component going outward and inward. These two guys are going to push apart, and this is going into tension. That's why it's red. And this is the kappa greater than 1. And if we make the kappa less than 1, there's the force chains, and the inside is going into compression. Okay. And this actually refers to the final exam question that I had in the course when I taught this some years ago, this type of stuff. And on page 4, it talks about this here, and it asks questions about that. It's too bad we're not having the course. You would have loved it. My exam, it was all like questions you had to think about and like write words. There weren't really any equations. And so you can look at this if you're interested. There's more discussion about this. But this is the key idea here. Okay. So going back again, this is also telling us, because in almost all real materials, certainly in all rock materials, the Poisson ratio that people measure in the lab is always bigger than 0. It's usually, again, maybe 0.1 might be the lowest I've heard of, and it's usually less than 0.5, maybe to 0.335 or something, which is telling us that a geomaterial, which fundamentally is made up of little grains glued together, that ratio of normal to shear stiffness is greater than 1. Okay, which is in keeping with what that little thinking of taking your hand and pushing down on your hand on the surface of your hand. It's stiff in the normal direction. It's not so much in the shear. So that's what most real materials are, which is telling you that when you're setting Kn and Ks in these models, you always want to have Ks smaller than Kn. And when you talk about a joint in rock, just a joint, people they find a big joint in a rock, and they carve out a giant core that crosses the joint, and then they do compression tests on it. And what they can then do is come up with what's sort of like the effective stiffness of the material on top and on the bottom, and they can pull out, there's also a stiffness just associated with the joint, because the joint, when you zoom in on it, is a whole bunch of messed up asperities that are getting squeezed together. And there's quite a bit of localized deformation there. So people talk about joint stiffnesses. This is a real measurable thing for any material, but in particular for our world of rock. And so this is a real thing they measure, joint stiffnesses. And what they find is that the Ks is always smaller than the Kn. Now, how much? I don't know exactly. What we tend to be, maybe it's like 2 to 4 times smaller. And so when people build big discrete models like this and they put in joints, they'll choose a Kn to like match their overall deformation response of that joint, and then they'll because usually you don't measure all these things in a lot of lab tests. And then if they set Kn to 1e to the 9, then they would set Ks to, divide that by 3, 0.3e to the 9. No one ever builds joint models that have Ks bigger than Kn. And so this is also an interesting thing after we did all this analysis some years ago, sort of a verification that it may make sense is that, oh yeah, in all these joints, we find that Kn over Ks is greater than 1. Okay. So any questions about this? I think it's kind of amazing. And this little example here, Peter Kundal came up with this way back, because he started thinking about these same things we were doing. Contact bond. Okay, how do we turn this into how do we choose Kn and Ks? Oh, let's look at this representative system like we did. And so the kind of fundamental thing that's going on here is it's the normal and shear stiffness ratio that's controlling how much the material bulks out. And of course, it's also a function of the packing and the shape. All these things are happening. This relation exactly holds only for a perfect packing of disks. Okay. And people have done some analysis, like sort of limiting analysis, where you take an arbitrary packing of these things and you can work out in this general way how Kn over Ks relates to the Poisson ratio you would measure. But you can only work that out for like simplified packings, not for arbitrary packings. But for arbitrary packings, by doing things like PFC, we build systems and we just vary Kn over Ks and run the test a bunch of times, and you can map out that curve of how the Poisson ratio is affected by this. Okay, but it's not a precise thing. So for a real model, for a real rock, because the Poisson ratio is a function not only of Kn, but the packing and everything else, you can't just magically dial in the Poisson ratio. Here's my rock. It has a Young's modulus of 2 GPa. It has a Poisson ratio of 0.3. Everybody knows that for any rock. You can't just directly, easily construct a bonded system that matches that Poisson ratio. You can easily get one that matches the E, but not the Poisson ratio because the shape and everything else. So you would have to actually reproduce the microstructure arrangement of that rock if you just wanted to have an exact match with Poisson ratio. Okay. Okay, makes sense? Kind of makes sense?
Yes.
Yes, okay. We're going to take a break. And yeah, this is like a key thing. Yeah, this thing about the deformability here. Right away, as soon as we move from a discrete system to a glued together system, we have to think about these mappings here. Okay. So we're going to take a break. And now what time is it? We'll take a 15-minute break. It's okay. It's almost 10. This is so perfect because we were in a bar and the guy was sitting by a pool table. It made me even more excited to show him this because I said, look, you can understand this. We're looking at the pool table and we're going to simulate that with this super cool model. Are you guys still there?
Yes.
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 Okay. So I'm going to run this thing. Here we go. PFC demo. Going to run this thing. Now, remember, this is 1995. This is PFC version 1. Okay. This was the state of the art of PFC. Now, I actually still have that executable, and it actually still runs on Windows. Okay, so I'm going to run it. And in fact, about a year or two ago, I told Dave Russell, who's the overall software architect of all Itasca software, and I said, I run this thing, and he just about passed out dead because he didn't think it would still run. So look at this. So here's PFC, call a data file. There we go. That's the data file. That's what we were looking at. So these guys are perfectly lined up. There's no bonding. And this is a guy that's given an initial velocity. There's no damping here either. So this is going to be like a pool ball getting shot into these guys. And so we'll just run this first. And boom, they all move apart, right? Isn't that exciting? So I was going crazy, like this is super exciting that we could do this. Now, but just wait. Let's talk about what's going on here. Let's do this one. Oh, just a second. I got to make sure this old PFC, you had to make sure you started from scratch. If we're lucky. Oh, come on. Well, let's just see what happens. Sorry. I think I do that first, and then I think I call this other data file. I want to run this slowly. Here we go. Continue. Here we go. Boom, I'm stopping it. I'm stopping it after just enough steps. And there you can see it. Those are the force chains. They're all black. There's no tension. They're all compression. And it's hitting. There's still a couple force chains here. There's still one here, right? But if I go a little farther, that's not going to be there. Now I'm going to run this again, and I want someone to tell me what we're seeing. Run me. Here we go. Oh, see it. This is not happy. Just a second. Stop. Hang on. Da-da-da-da-da. File call. There we go. Now, what are we going to be seeing here? Watch. What you're going to see here is you're going to see it's going to hit that thing, and a compressive force is going to build up at that contact, which is going to make that ball that it's touching start to move, which is going to then push against the other balls, which is going to make compression build up. And what you're actually going to see here is a compressive wave going through the system. Okay. And they're not bonded. So the wave just goes through and they all move apart. So let's just watch that then. That's what I just said. Continue. Boom. And I'm just pausing. Force builds up, gets really big force. And see that wave going through? See the big thick chains? They're going all the way through and they're going out the other side, and they're not connected, right? So it's just a granular system. Compressive force goes through and we're done. Okay, with me?
Yeah.
Yes.
Okay, so to summarize, unbonded compression, key element, tension cannot develop. You have to have some concept of stickiness, which we're going to call a bond, in order for tension to develop in a material. It's fundamental. And sometimes granular materials get tension too. They may have surface water in there, and then there's capillary forces between them. That's why if you go to the beach and you take a pail of sand and turn it upside down and lift up the pail, well, first of all, if it's dry, it doesn't sustain tension. It just sloshes down. But if it's wet a little bit and you lift up the pail, it just sits there. And that's because there's surface tension. So there has to be tension to develop. There has to be some kind of stickiness, right? And here we go, and it goes apart. Now, let's put in a bond. This is thinking about that contact bond, right? It really, the key thing in terms of strength now, in terms of bonding, is it has a tensile strength and a shear strength. That's what these guys are, right? And of course, it has the linear behavior, the Kn, the Ks, and the friction. And notice I'm mentioning here, it's as though you had a tiny dot of cement here. It doesn't resist moment. In order to resist moment, there has to be a finite width so that it can build up tension and compression on the inside and outside, okay? But let's say we do this, and then this is the concept of a contact bond, which we talked about the other day, right? Linear model to begin with. If it's bonded, you cannot have a gap. You have a fuse. It can break in tension. In the shear direction, you do not have frictional sliding. You have a fuse. It can break in the shear direction, right? After it breaks, it's linear. This is just showing that. So what's going to happen now if we do this? So now we're going to call the exact same system, but this time it's bonded. And we're going to look at the force chains. Watch this. Tension. Now we expect to be able to get some tension. And I'm setting this to no damping, and I'm setting this to infinite strength, so it can't break. The only difference here now is it can sustain tension. So we're going to see black for compression, red for tension, no damping. So once this guy is going to apply work to the boundary of this thing, that's going to get stored in the system as strain energy. Okay. And there's no energy dissipation here. So once that system gets some strain energy, it's going to always have that in there. And we'll see what happens. So what's it doing? What are you seeing there?
They are bonded, like
They're bonded. And how's it behaving? How is it different from when they're not bonded?
as a one system compared to a granular behavior.
That's the first thing, correct? It's one system, and you put energy in it, and it's not getting dissipated. What's this business about? It's sort of like glomping back and forth. Let's run it again. What's going on here? Tension, compression, tension, compression.
Equilibrium.
Sorry?
I was thinking they are like the forces in equilibrium,
Well,
like
uh-huh.
compression and tension within the system.
That's right. Think about, remember I said there's a compressive load that's getting pushed through this thing. Let's look at this more closely. Now I'm going to run it slowly. Continue. Hopefully it'll stop just before it hits. There we go. Now watch, compression. And now it's building up tension right there. This is a compression wave. It's finally made it to the other side. But because it can sustain tension, that compression wave bounces back. And this compression tension system just keeps on going back and forth here. And so this is an elastic body. It's got a whole bunch of springs. This is that physical set of tennis balls with springs between them. And you can see how when you hit that thing, that's a wave. It's a wave, a compression wave passes through, and when it starts to build up, it causes tension all over the place. And so this is a dynamic system vibrating back and forth. This is a solid body. It's behaving like a solid body. And it's dynamic. And so you can see then, if you can imagine now, if I had finite strength, right? This could then break at certain points. And now it breaks up into two bodies. And each body, though, is this dynamic thing. This is what happens in a real material, in a real solid body. You're putting in that wave. In a real solid body, there's dissipation. There's a damping that occurs. And so that wave loses energy, and eventually it stops bouncing around. Okay. So I really like this because this is what's happening in these discrete systems. The stiffness is because of those springs. And that's the same thing that's happening in a sandstone. There is a stiffness between the particles. Okay? Does that make sense? Do you have any comments, any questions? I mean, this is it. Everything else just flows from this. Okay? And this is stressing the fact that these things are fully dynamic systems. You know, it's conserving momentum. It's, you know, this is not just a quasi-static thing where you apply a load and it deforms and you're done. This is when you apply a load, it's hitting, it's impacting, and there's an impulsive force, and that force is pushing into the material, sending a compression wave. Like if we were sitting at a dinner table and you were on the far side and I was on one side, and if I pounded my fist against the table, if you had your hands on the table, there would be a finite amount of time it would take, and you would feel that compression wave, that vibration. And that vibration compressive wave would actually bounce off the free surface and come back. And, you know, eventually it will dissipate. So this is what's happening. This is stressing. This is modeling all of the proper physics, including the dynamic physics of these things. And if you choose the microstructural properties, the stiffness ones, such that you have the E and the nu of a real linear elastic isotropic body, and if you have the real mass in there, meaning the real density, for a linear elastic isotropic body, we can look at the dynamic response of such a body, and what we find is when we load the body rapidly, we get a dynamic compression wave that goes through, and it moves at a certain velocity. We call it the P wave velocity. And some of the motion is also in a shear mode, and they call that an S wave. And these are real things that people measure. And so the P wave velocity in like a sandstone is, I think it's around like maybe 3,000 meters a second. And the shear wave velocity is always less, like maybe 1,200 meters a second. PFC will reproduce all that. If you have the proper E and nu, and if you have the proper density of the real system, you will get the same wave speeds. Okay. People use PFC to their advantage because of that. Oftentimes, when we try to understand damage around a real excavation, one of the ways we can do it is by essentially pounding on the rock and putting sensors a little bit farther away and measuring the P and the S wave velocities. And from those, we can back calculate the Young's modulus and Poisson ratio. And the more things get damaged, the lower those velocities are. And so all of that stuff is, that's how we often do it in the field. It's a non-destructive way of measuring damage. And so people have modeled that kind of stuff directly with PFC, bonded particle models, and tried to get some correlation. Also, people have looked at what they call acoustic emissions. If you have a rock, let's say we have an excavation, and we look at like the face of the excavation. It's a big giant tunnel, and it's 2 meters wide, and we're slowly boring it forward, and there's a face. We could walk to the end and we bump our nose against it. That's the free face. And then we somehow do something to excavate it and move it forward. As we do that, we're causing damage ahead of that face, maybe by a diameter or more of the excavation. And so people can try to understand that damage and locate it by the fact that when you load a rock and you cause a breakage internally, it sends out an earthquake. So just like in the earth, when you have a high stress underground and suddenly there's a rapid slip, some kind of breakage, that means there's a rapid motion, which means locally there's a big force, just like this big force here, and it sends out a compression wave into the material. That compression wave is then measured at these different seismic stations around the world. And if you have a sufficient number of stations spaced out in space, each one gets an arrival time, and you can then back calculate where the earthquake occurred. And you can also back calculate, depending upon the energy in that wave, the magnitude of the earthquake. And that's how they do these things when you get an earthquake, and they talk about magnitude and all this other kind of stuff, and they talk about source location. If you can do the exact same thing for a rock specimen or for an excavation, it's just a smaller scale. And so for a big excavation deep under, for an earthquake, those waves have a very low frequency and they travel really, really far because they're very high magnitude. If you have a tiny crack in a specimen, it goes faster. Not faster. It has a higher frequency, and we can still though do all the same processing. So what they do, for example, is they might take a cylinder of rock in a lab, and they put little tiny transducers around the sides of it, around the outside. Those are little earthquake sensors. They're accelerometers. And then as they do the test, you keep hearing these pops and cracks because there's micro cracks forming. And each time one forms, it sends out a little compressive pulse. And so those acoustic sensors, those accelerometers measure that. So they're sitting there, nothing is happening, and suddenly, boom, they get this big spike in motion, and then it dies out. And so you can, again, then back calculate where the damage occurred. And so this is called acoustic emission monitoring. And this is one of the ways that we can understand the evolution and properties of damage that's forming in a rock that's being loaded, like in compression, for example. People also do this for hydraulic fracturing. You're hydraulic fracturing, but you have these accelerometers all over the place, and you're just listening to them. And as you hydraulic fracture, you want to know where the cracking is happening. So by looking at these acoustic signatures all over the place, you can back calculate where all the action is. So this is the thing. So we use the fact that waves go dynamically through a material. And again, many people have used bonded particle models to study different aspects of that phenomena. Okay? Good.
Okay.
Make sense?
Yep,
Okay.
got it.
Okay, excellent. And so here, what did I want to say? Bonded, compression, and tension. There you go. You can do this in 3D and screw around with it, and then what'll happen, well, I'm not doing it here, but it could, like, move around and things. Okay. Well, since we're here, this is kind of the next step, and we'll talk about this in a different way in a moment. But carrying on, if we have that simple thing, we can have a little bit more sophisticated type of bond. And now, instead of just having a tiny bit of cement, we're going to conceptually have a giant finite size. Notice there's a length scale here, the radius, the size of the bond. And this contact model was set up to behave as though you had cement. Look at it from the side. This red is actually cement, okay? This cement fills space. This cement has a stiffness, by the way. If you take a bunch of sand, you can squeeze it in an odometer test and measure its stiffness. If you then pump in cement and let it set, it's going to have a higher stiffness because the cement is also contributing stiffness. Okay. So that means this particular model, it's also going to have stiffness. It's going to have cement stiffness in here. It's going to have the linear behavior for the two surfaces touching. So it'll have those properties. But if there's cement, it's going to do this. So the cement has a radius. The cement's going to have stiffness. And the general idea of stiffness, remember, is a Kn and a Ks, which we're going to relate to an E star and a kappa star. And then there has to be some concept of breakage. And so here's what we're going to have. We're going to have, for a parallel bond, a radius. We're going to have a normal and shear stiffness, and we're going to have a concept of a normal strength and a shear strength. And so notice it's saying it's like additional material that got deposited after the balls were in contact. So you make a packing, a granular packing to start with, and then you effectively inject cement, which means you add the bonding. And now, because it has a radius, it can resist moment. Okay. And then it has a concept of breaking, right? And it's behaving like, again, glass beads cemented with epoxy, where the epoxy is not just at where it's touching, but it has a finite size, which you can see here. And the parallel bond, actually, this is a very good representation of what the parallel bond is doing. Okay. That's all we're going to say, because we're going to talk about it in the other slide set. And here's what we're going to do now, because we only have 15 minutes. Instead of trying to think this out, because we could start, we were going to like just play with this bonding now, but we're not going to have time to do that. So we're going to first instead, let's just move on. Let's just talk about these contact models. And then when we come back next week, we're going to actually build simple models with these, and we're going to look at, let's change E star. How does it affect this? Let's do a UCS test. It's going to turn out we have this thing called a material modeling support package that makes it very easy to create specimens of bonded material and then to perform tests on them. Very easy. So that's what we're going to use, and we're going to play with, these things. Okay. But we still need to talk about these bonding concepts. So this is a good, just a 15-minute overview. So what about adding bonds? Here we go again. One more. We talked about this before. I just talked about in the last slide set. We start with the simplest one, contact bond, linear model. Those are the parameters. Pretend that this radius of this system was actually 0. And if you did, you would come up with a contact bond. And notice we, instead of a gap, it can take load. Instead of a friction, it has a strength. If either one breaks, boom, it's gone. Turns into linear model. It's as though if either of these breaks, all of this material is completely removed. Well, there is no material hardly because it's a point thing. Okay. But it can't sustain tension then anymore, or shear, because it turns into a linear system. So again, the review again, the linear model, move it down, build up a normal force, normal stiffness, no tension. Let's go to the contact bond. Here we go. Now you have tension that can build up and you have a strength. And if it breaks, boom, load goes to 0. You go back here, linear model, that's the shear stress, shear force, loads up at KS, has a critical value related to the normal force and the friction coefficient, and then it slides. If you keep on forcing it this way, the force just stays the same. If you then push it back, it starts unloading on the same slope. And if you go back again, it goes back up this curve and continues. Okay. Now the difference, if it's bonded, now you have a shear strength, and so it loads up the same way, but then if it reaches the strength, it doesn't slide frictionally, it just breaks. Boom. Load goes to 0. And now it's the linear system again. Okay. So this is that simple model. Okay. This is the soft contact thing we talked about. And now let's talk about the parallel bond. So think of, you can come at it this way. This guy is so small, it doesn't resist moment. Let's pretend it wasn't so small. So instead of having a sandstone with quartz grains that are near spherical, that are just barely cemented, let's pretend there was a lot of cementation that occurred. That sand got buried, and over geologic time, something happened and carbonate precipitated in a lot of it, and we got a finite width bonding. That's going to be this parallel bond. So again, if it's not bonded, it's the linear model. If it is bonded, it's a little different. Now let's unpack this. This is a simple idea. Look at this. This is the linear model. It doesn't know about width. It's just that this think of this radius here as approaching 0. It's supposed to be this. If the radius approaches 0, it's just this local thing interacting. So if I rotate this, it doesn't resist moment. So that's the linear model. But now it actually has a finite width. So think of this surface as being glued on to there and the green being glued on to there. And now it has a R bar radius. And what's going to happen is there's additional stuff. So here's the linear. This is still active. These things all matter. There's still force being carried across that little thing because we started with that force. We pushed them together. We got force, and now we put in cement. So this is all still there, but now the cement adds new things. So what does it add? Here's the linear part, still there. But now there's an additional stiffness, and we're going to denote a bar on top of the parameters to mean it's related to the bond. So there's an additional spring, which is the stiffness of the cement. And that cement has a fuse that has a strength that can break. So because there's a fuse, it can go into tension. I can pull this apart. The cement goes into tension, and it can break. And so we call this a parallel bond because it's two springs now acting in parallel. And in the shear direction, there's still frictional sliding that can occur at this little point where the surfaces are touching. They can slide frictionally. But in addition now, this big giant area that's glued together, this bond, is going to have an additional stiffness, a shear stiffness, and it's going to have a concept of a fuse that can break. And the strength of that fuse is going to be related to what we're going to specify it not just as a single strength, but as it's related to the cohesion and friction angle of some material. That'll give us the shear strength. I'll show you that in a second. Okay. So again, the parallel bond can be thought of as that red stuff. And when the bond breaks, you're only left with the surface-surface interaction. That's the linear model. And the forces that were carried in the cement, right? The forces in this spring and that spring, those are forces. They're being carried. They just are gone. So if I took this system here and I pulled these two guys in tension, so they weren't even touching anymore, but there was load in that thing. It's like a big rubber binder. It's carrying load. If it breaks, that load is gone. Okay, that's what's happening with the parallel bond. When it breaks, that load is gone. And of course, while it's here, it can resist moment, but when it's gone, it can't resist a moment. Okay, so how does it break? We're going to have a very, very simplified concept of breakage. Okay, we're going to go back to here. See this? It's as though we had a surface. So this thing right here is modeled as though you had one on this side that's stuck out and one on the other side that's stuck out, and we have an interface between them. That's how we're modeling this. There's an interface. And if I rotate this to the clockwise, this side goes in compression, this side goes in tension, those two interfaces. What we're going to do is look at the tension in the outer fiber right here, because that's the highest tension. Because I just rotate this like this, that's the highest opening, that's the highest tension. Tension gets less, less, less. It's compression on this side. We only look at that. That's the thing that we compare to the tensile strength right there. Okay. And for the shear, we look at the overall shear force on this whole interface. And if it reaches the shear strength, it breaks. And so that's what we've got here. If this outer fiber stress, sigma bar max, is greater than the tensile strength, it breaks. And we're going to keep track. It's either going to break in tension or break in shear. And this is the maximum shear stress on the outer fiber. Okay. And remember, when it breaks, it's gone. So it's a crazy breakage, because in reality, for most materials, it might not just instantly do that. It might start to break here. And then maybe a little crack is forming as you bend it. But that's not going to handle here. This is really simple. Okay. Shear strength. Remember, fuse. There's the shear fuse. So its strength is in terms of a cohesion and a friction angle. What does that mean? It means this. Here's the shear strength, strength of the fuse. This is the compression between the surfaces. There is a thing called a friction angle. If you increase the compressive load between them, it's stronger in shear. And if you don't compress them and pull them apart, eventually it'll fail in tension. That's what this is. And this crossover point is what we call the cohesion. It means if you had these surfaces interacting and stuck together. If you have no compressive load on that interface, that's the strength. That's what we call the cohesion. Most geomaterials, if you take them and squeeze them together, the harder you squeeze them together, the stronger the shear resistance. And so that's why we have a cohesion and friction as a parameter here. Okay, we don't just specify the shear strength. This is again a difference. The contact bond is simpler, has a shear force. We're done. Doesn't matter if you squeeze it together. Shear force is shear strength. I mean, shear strength is the same. Okay, so this is how we get the failure. And there's another super important parameter here, which is what we call the radius multiplier. And what that's going to do is determine the size of the cement, the width of the cement. Because it's going to turn out that the stiffness, for example, that we specify is actually stiffness per unit area. That's what you have when you have a joint. We think of this as a joint. These are two interfaces. It's a joint. A joint is an interface between two things. And we say this, there's going to be a stiffness per unit area. And so you take that stiffness per unit area and multiply it by the area, which is related to this. Okay, so when you have an interface, you don't specify a direct stiffness in force over displacement. You specify a stiffness per unit area. So, because if a joint, if this area is bigger, the overall stiffness is bigger. Okay, so this is the thing. This will go between 0 and 1 usually, and it's related to the size of the two guys in contact. And so it's basically the minimum of these. So here you have this guy smaller than this guy. So this is the fraction of this length. So if you make that 1, it goes all the way out to here. As you make it less than 1, it shrinks it in. Okay. So those then are the parameters of this model. There you go. The width of it, the normal and shear stiffness per unit area, the tensile strength, and instead of a shear strength, there's a cohesion and friction. Okay, and I think that's it. Yes. So are there any questions? Get the base. Tell me. Make sense?
Does that make sense?
Okay. This was the second model that we came up with after the contact bond had been created and exercised on all kinds of geomechanics problems, and there were things that it didn't behave like a lot of rock because it only behaved like sandstone with nearly circular grains that have tiny amounts of cement. So this was an attempt to say, what if you actually have finite hunk of cement in there? And we called this the parallel bond, tried to keep it simple. So it has, but it's now suddenly, as soon as you start putting in more mechanisms, you have to have more parameters. So there has to, now there's a concept of stiffness, and that's the stiffness of the cement itself. So that's a new parameter, right? How big is the cement? How wide is it? That's this parameter. And then we have to have an idea of strength for it to break, right? So right away here, now you got 6 parameters for the cement and you got 3 parameters for the linear model. So this thing, this seemingly simple model already has 9 parameters. And of course, it's also the overall behavior is a function of the shape and the packing of these things, okay? Just as an introduction to next week, this model then got released into the wild, as we say, because we started selling PFC. We did this research, we started selling PFC, and all these rock mechanics people started buying it and using it to do research. And this model behaved like a lot more kinds of rock. Like it behaved like a sandstone that had finite length glue between it, right? That's really what it behaves like. So there's a lot of rock that can be approximated that way, but there's a lot of rock that can't. And in particular, a very well cemented sandstone or a granite, they have a fundamental property in rock mechanics that people believe is an important thing, is not only is the tensile strength of the rock, now I'm talking about the macro scale, a specimen. So if you take a rock and you don't know what it is and you say, what's the fundamental thing I need? Well, what you would do is you do a direct tension test and you measure the stress at which it breaks and you call that the tensile strength. And then you do a UCS test and you measure the initial slope and you get a Young's modulus and you look at the expansion and you get a Poisson ratio. And then you keep doing the UCS test until it breaks and you call that the UCS and you call that the strength. And so people then say for a typical rock, it has a tensile strength and a UCS. You always can measure these. And then you say, oh, first of all, what you find is that UCS is always higher than the tensile strength. Rock is very weak in tension. So when you pull it apart, it might break at 10 MPa if it's a granite. And if you do a UCS on that same specimen, it's not going to break until 200 MPa. And so now you've got this ratio of UCS to tensile strength of 20. And if it's weakly cemented sandstone, that ratio is going to be like 3. And if it's super well cemented granite, that ratio might be as high as 32. The more well connected the rock is, the higher its UCS is, but it's still weak in tension, is what we find. And so what people then found is all these people took these parallel bonded, this is all they had. So the question is, what's this going to behave? Can you choose? Think of this as a parameter space. There's this incredibly complicated parameter space of how is the macroscopic response? What is the possible range of macroscopic response? And what can you possibly get by playing around with all these different combinations and combinations of shape and combinations of packing? That's a giant parameter space, and there's a wide range of response you can get. And what people found is that for this parallel bonded material, no matter what they did, they could never get a ratio of UCS to tensile strength that was bigger than about 5. And I can show you dozens of journal papers of people trying things and failing, including Peter Kundal and me. We had all kinds of hypotheses. Oh, I think it's this. What if we just do this? Didn't work. What if we do this? Didn't work. And so this, for many, many years, this was a big, if you could think of it as a limitation, right? This microstructure that we have is only going to behave like kind of partially well cemented sandstone and not like granite, for example. Okay. Nonetheless, huge amount of papers were written and people did stuff with this and used it for all kinds of research. And then what they would do is they'd say, well, I cannot match both the UCS and the tensile strength, so I have to choose one, and I'll just match one, and then I'll do my whatever I'm going to do with it and see what I get. So that was a limitation, and I'll talk about at the next lecture in 2 weeks. We then gave this a lot of thought and came up with an idea of what we could do to also get the high ratios. And of course, what you have to do has to relate to the real microstructural physics of why that rock has a higher ratio. And once we discerned what that mechanism was, it was a relatively straightforward process to put that mechanism into a new contact model. And that's what we call the flat joint contact model. So we'll talk about that at our next lecture in 2 weeks. Okay?